In many instances, the objective of sampling is to estimate a population proportion. For instance, an accountant may be interested in determining the proportion of accounts payable balances that are correct. A production supervisor may wish to determine the percentage of products that are defect-free, and a marketing research department might want to know the proportion of potential customers who will purchase a particular product. In all these instances, the decision makers could select a sample, compute the sample proportion, and make their decision based on the sample results. The population and sample proportions are computed by taking the number of items of interest and dividing by the population or sample size. Sample proportions are subject to sampling error, just as are sample means. The concept of sampling distributions provides us a way to assess the potential magnitude of the sampling error for proportions in given situations. This is computed by taking the difference of a sample proportion and the population proportion. In many instances, you'll be interested in determining the portion P of all items in a population that possess a particular attribute. The best estimate of a population proportion will be P, the sample proportion. However, any inference about how close your estimate is to the true population value will be based on the distribution of the sample proportion P, whose underlying distribution is the binomial. However, if the sample size is sufficiently large such that n times P is greater than or equal to 5, and n times 1 minus P is greater than or equal to 5, then the normal distribution can be used as a reasonable approximation to the discrete binomial distribution. Providing we have a large enough sample size, the distribution of all possible sample proportions will be approximately normally distributed. In addition to being normally distributed, the sampling distribution will have a mean and standard errors indicated by the equations in this slide. In the previous section, we introduced Theorem 4, the central limit theorem, which indicates that regardless of the shape of the population distribution, the distribution of possible sample means will be approximately normal, so long as the sample size is sufficiently large. Theorem 5 is similar, but pertains to the sampling distribution for the sample proportion. Also similar to the last section, we can use this equation to convert the sample proportion to a standardized z-value. Here's a simple random sample with n equals 100 and x equals 73. The population proportion is 0.80 and the sample proportion is 73 over 100, 0.73. So the mean here is 0.80 and the standard error, or the standard deviation of the sampling distribution, is 0.04. Our event of interest is the probability such that p bar is less than or equal to 0.73. So we standardize the z-value, which we get a negative 1.75, and use the normal distribution table or Excel to determine the probability. The resulting probability is 0.0401. Go ahead and open Excel file Gillette and answer the following questions. So to do this, I'm going to insert a pivot table as we've done before. So from this problem, we know that nationwide, 66% of eligible workers participate in these accounts. So here, P bar will be 0.72, and our population will be the 0.66, so we have a sampling error of 0.06. Okay, so now we want to determine the probability that a sample proportion at least as large as that obtained in the sample would be obtained if Procter & Gamble workers have the same proportion of participants in 401k accounts as does the rest of the nation. So we know the mean obtained in Part A was 0.72, and the population mean is 0.66. So now we need to determine the standard error given by sigma sub p bar. So we see the standard error is 0.0335 in this case. So now we need to determine that the probability of p being greater than or equal to 0.72. So to do this, I'm going to insert a norm.dist function with 0.72 being the mean that we found earlier in Part A, 0.66 being the population mean, and our standard error being the standard deviation in the norm.dist function. Again, cumulative, and since we want greater than or equal to, we'll do a 1 minus to yield a probability of 0.0366. So we see that it's very unlikely that a sample proportion will be greater than 0.72. given a population proportion of 0.66. So we can say that participation rate in the 401k plans for Procter & Gamble workers is larger than that for the nation as a whole.